Now we're going to look at a scenario where you receive some payment V each period, this period, the next period, 2 periods from now, and so on, up to period capital T. And we want to know what the present discounted value is of this stream of payments, where each payment is identical. Each payment is equal to V. V might be $100, V might be $200, whatever the amount is that you're getting every period, that is denoted by V. Okay, so the present discounted value of the stream of payments is the amount that you get today. That's not discounted because you're getting it right now, plus the amount that you get next period, divided by 1 plus R. So now we're discounting the payment received next period because we're not getting it for a period. Then we're going to add to that the amount received 2 periods from now, and to appropriately discount that, we're going to divide it by 1 plus the interest rate squared, and so on. Right? It's the same thing 3 periods from now and 4 periods from now, and so on. It goes all the way out until T periods from now. Okay, so now what we want to do is we're going to want to come up with a formula that will help us solve for what could be a large sum of different terms. To help us do that, the first thing we're going to do is we're going to introduce some new notation. So I'm going to introduce this term delta here, and it's going to be equal to 1 over 1 plus the interest rate. Okay, so that just makes this present discounted formula for the stream of payments look a lot nicer. Before it was V plus V over 1 plus R plus V over 1 plus R squared. With this change in notation, the present discounted value is V plus delta squared V, so on. Okay. So this is going to help us have less messy notation as I'm showing you this trick to solve the problem. Okay, so you can see here I've rewritten the present discounted value. It's equal to the amount you receive each period, V, versus V, then is plus delta times V to discount that the amount received 1 period from now. Note the fact that it's not worth as much as the amount received today. You'd rather have it today. Plus delta squared times the amount V you received 3 periods from now, plus delta cubed times V, and so on. Now what I'm going to do is I'm going to change this, and rather than have say this equal to present discounted value, I'm going to introduce a variable S that is going to be equal to the present discounted value. And you're going to see why this is useful in a second. What we're going to do is we're going to go through a couple steps, and then we're going to solve for S, which we know is equal to the sum, which is equal to the present discounted value. Okay. So before I do that, I want to write down what would happen if you were to multiply S by delta. Delta S is simply equal to every term in S multiplied by delta. So the first term in delta S is the first term in S, which is V, multiplied by delta. The second term in delta S is the second term in S times delta. So delta times delta V is equal to delta squared times V, and so on. Now this goes on forever in both of these because we've assumed it's an infinite period problem, at least so far. So you get this payment V every year for the rest of time. Okay, so now here's the trick. What we're going to do is we're going to subtract delta S from S, and then we're going to solve for S, which we know by how we've defined it is equal to the present discounted value of this stream of payments. Okay, so let's write S minus delta S. And that's going to be equal to all the terms in S minus all the terms in delta S, that's what delta S is equal to. Okay. Now here's the cool trick. If you'll note, first term in delta S is the negative value of the second term in S. So the first term in delta S cancels the second term in S. Likewise, the second term in delta S cancels the third term in S. And so on. In fact, every term in this infinite stream of payments is going to be canceled by the analogous term, the other stream of payments, except this first term in S. since every term in S is multiplied by delta when you're coming up with delta S, this first term does not appear delta S. So this is the only term that remains after such canceling. So we have S minus delta S is equal to V. It's the amount that you are paid each period. Now remember, what we want to do is we want to solve for the present discounted value. And we use the variable S to denote the present discounted value. That is, we replaced the present discounted value with this variable S. So that means that if we can solve for S, that will be equal to the present discounted value. So note that this left-hand side, S minus delta S, is the same thing as S times 1 minus delta. Okay, that's still equal to the right-hand side. And so if we divide both sides by 1 minus delta, that tells us that S is equal to the payment that is received each period divided by 1 minus delta. Okay, so rather than sort of adding up this infinite sum or trying to come as close as we can to approximating in Excel, we know that we can just come up with this very simple analytic formula. If you receive a payment V each period starting today, the present discounted value of those stream of payments is simply equal to the amount that you receive each period divided by 1 minus delta. Well, remember, delta is equal to 1 over 1 plus the interest rate. And now let's do the same thing, but rather than having an infinite series of payments, we're going to have the first payment received in an arbitrary period T, and the last payment received in an arbitrary period capital T. Okay, so this is what the present discounted value in this more general form looks like. Okay. Now we're going to solve it using the same steps. It's going to be pretty similar. There's going to be a couple of small changes. Okay, so let's start by writing delta times S. Okay, so what's the first term in delta times S? Well, it's the first term in S multiplied by delta. Exponent on delta is going to increase by 1. The second term in delta S is going to be the second term in S multiplied by delta, which is delta to the T plus 2 times V, and so on. The last term in delta S is going to be the last term in S multiplied by delta. So it's going to be delta raised to the power of capital T plus 1 times V. And we're going to do exactly the same trick. What we're going to do is we're going to subtract delta S from S. We're going to say what that's equal to in terms of these equations. And then we're going to solve for S, which is what we know is a variable that represents the present discounted value. Now, again, you're going to find that the first term in delta S is the same as the second term in S. Since delta S is subtracted from S, they are going to cancel. So we can cross that one off and cross this one off. And the second term in delta S is going to cancel the third term in S, and so on. Now, the only terms that are not going to cancel, that there's not an analogous one in sort of the other expression, is the first term in S, like before, and the last term in delta S. There's nothing to cancel that one out. Okay, so if we simplify this, we can say that S minus delta S is equal to delta raised to the T times V. So first payment is received T years in the future, so we have delta to the T times V, minus the last term in delta S, which is delta raised to the capital T, denoting the final period, plus 1 times V. Let's simplify both the left and the right-hand side a little bit further. S minus delta S is equal to S times 1 minus delta. And if we simplify the right-hand side, and then we can divide both sides by 1 minus delta, yielding that S is equal to this thing divided by 1 minus delta. So now we have a general formula that will apply to any stream of payments, where the first payment might be in any arbitrary period t, and the final payment would occur in period capital T. Now you'll notice that you could use this formula to solve for the infinite period problem. Your first payment is received today. In that case, if the first period is received today in period 0, delta raised to the power of 0 is simply 1. And delta, which is a number that's less than 1, you raise a power less than 1 to the power of infinity, it goes to 0, which would give us exactly the formula that we had before. For an infinite stream of payments that starts today, the present discounted value is V over 1 minus delta. But this more general formula would also be one you could use for any first period payment occurring in period T and any last period payment occurring in period capital T.